Section 14.7 Centrifugal Distortions. Although the above selection suggests that rotational spectra are very simple, complications arise because molecules are real systems, not ideal ones. Although the application of the ideal 3D rigid motor system uh, to molecule works very well, it does not do a job perfectly uh, in describing rotational spectroscopy. Perhaps the biggest single non-ideal factor for the rotational spectroscopy is the fact that molecules are not rigid rotors. It is assumed, for example, that no molecules have a certain specific unchanging bond distance. This is not the case. As molecules have larger and larger J quantum numbers corresponding to the higher and higher energies, they distort slightly, but enough to change the energy levels noticeably away from the ideal values. This effect is called centrifugal distortion. Consider the diatomic molecule in figure 14.16a. As it rotates with a relatively low J quantum number, the chemical bond is strong enough to keep fairly constant bond length. However, as figure 1416b shows, at large J, the rotating molecule is distorted as the spinning atoms experience a sort of centrifugal force, like we feel on fast-spinning merry-go-rounds. This force contributes to the slight lengthening of the bond distance. The, the, both distances appear on the denominator of the rotational constants used to define I, the moment of inertia. This is the lengthening of the bond and therefore serves to lower the total energy of the rotational state. So instead of the rotational spectral lines being exactly 2b apart, they begin to get less than 2b apart. The centrifugal distortion thus observed as shrinking of distances between adjacent lines and additional spectrum. The effect on the rotational energy of centrifugal distortion is proportional to J parentheses J plus 1 all squared instead of J times J plus 1. Indeed, if the centrifugal distortion depended on J times J plus 1, uh, it would be worked into the B rotational constant. What is usually done is to mathematically fit the rotational energies to a general equation having a form such as the one in equation 14.25. The energy of rotation is equal to B times J plus 1 minus D sub J times J squared times J plus 1 squared. Where D sub J is the centrifugal distortion constant, it is usually expressed in the same units as B, either in megahertz, gigahertz, or for frequency, or centimeters to the negative first for a wave number. The positions of the rotational spectral lines are therefore given as E of J plus 1 minus E of J, which is equal to delta E of rotation, which is equal to 2B times J plus 1 minus 4D sub J times J plus 1 to the third, equation 1426, where, as usual, the quantum number J refers to the quantum number of the low energy rotational state because the centrifugal distortion is less than the diatomic molecule bond. It is stiffer and therefore has a higher vibrational frequency, which will be introduced in the next section. The centrifugal distortion constant is often approximated by the following expression. D sub j is approximately 4b to the third over nu tilde squared, equation 1427, where nu with the tilde is the wave number of the vibration in centimeters to the negative first power, and B must also be expressed in centimeters to the negative first power units. Equation 14.26 shows the energy difference between rotational levels. Energy differences are what spectral lines measure, after all, and they deviate by a factor based on a third power of rotational quantum number J. Table 14.2 lists some experimental B and B sub J values for several diatomic molecules. D sub J is typically very small, so effects due to centrifugal distortion are usually noticeable only if the higher spectra for rotations of small molecules like hydrogen, or if very high energy rotational states are being probed. Diatomic and linear molecules aren't the only molecules that experience centrifugal distortions. Figure 1417 shows diagrammatically what happens to a water molecule when it rotates at high values of J. The atoms are forced to spread out somewhat due to the centrifugal distortion, and this affects the values of rotational energy, as depicted in figure 1418. For prolate and oblate symmetric tops, however, the situation is somewhat more complicated because there are two different moments of inertia, and therefore two series of rotational spectra as the molecule is distorted about one rotational axis. It affects the moment of inertia in the other axis. Centrifugal distortions of nonlinear molecules are, therefore, extremely complicated and will not be considered here. Section 14.8. Vibrations in molecules. For a molecule having n atoms, it is necessary to use an x and a y and a z coordinate to describe the positions of each atom. And so, such a molecule requires a total of 3 n coordinates to describe its position in space. Such a situation is shown in figure 1419. For changes in position, the number of necessary changes in coordinates is the same. For a molecule having n atoms, each atom's change in position can be broken down into a change in x, a change in a y, or a change in z coordinates. These changes are simply written as delta x, delta y, and delta z for each of the n atoms. These changes in coordinates may have different values, so an n molecule needs a total of 3 n changes in coordinates to describe its motion. Such a situation is shown in figure 1420. Note how this corresponds with figure 1419. Because the atoms are free to move in 3n different independent ways, we say that the molecule has 3n degrees of freedom. It turns out that we can choose the coordinates so that the combined motion of all atoms for 3 of the 3n ways corresponds to all of the atoms moving in either x, y, or z directions. That is, they describe translations of a molecule as a whole. Figure 1421 shows these 3 translational degrees of freedom. Since the entire molecule moves in space, we can describe these motions as translations of a center of mass of a molecule. In translational motions, the atoms of a molecule are not moving with respect to each other. These same changes in coordinates can simultaneously be chosen so that 2 for a linear molecule or 3 for a nonlinear molecule of the components combined motions of all the atoms correspond to rotations of the molecule about the molecular axis. Figure 1422 shows these rotational degrees of freedom for linear and nonlinear molecules. For rotations, as for translations, the atoms of the molecule are moving together in such a way as to move the molecule. Unlike translations, In rotation, the center of mass of a molecule is not a moving space. However, like translational degrees of freedom, again, atoms are not moving with respect to each other. This leaves either 3n minus 5 for linear molecules or 3n minus 6 for nonlinear molecules, combinations of motion of atoms of the molecule. In these combinations, the atoms are moving with respect to each other, but the center of mass of the entire molecule does not change. These internal atomic motions are vibrational degrees of freedom, or more simply, the vibrations of a molecule. There are many ways to describe the possible motions of an atom in a molecule. However, the mathematical treatment of vibration shows that there will always be a way to assign the changes in coordinates such that all of the possible motions of the atom can be broken down into 3n minus 5 or 3n minus 6 independent motions for each frequency of the atom's vibration, which is exactly the same. Such coordinates are called normal modes of vibration, or just normal modes. In vibrational spectroscopy, the frequencies of the vibrating atoms in the molecule are probed. The changes in energies of the vibrations are such that the radiation typically used is in the infrared region of the spectrum. Hence, IR spectroscopy is usually synonymous with vibrational spectroscopy. Very low frequency vibrations will be detected in the microwave region of the spectrum, whereas high frequency changes impinge on the visible spectrum. As with spectroscopy, the wave number, centimeters to the negative first unit, is common, but it is also the unit that describes wavelength of the light involved, usually expressed in micrometers or microns. Why do linear molecules have a different term, 3n minus 5 instead of 3n minus 6, for example? Recall that linear molecules have no defined rotation in their inner nuclear axis, so they lack a rotational degree of freedom. This lack is made up for by having an extra vibrational degree of freedom. We will find that linear molecules have at least one vibration that moves perpendicular to the vibration of the same frequency, and therefore have the same energy. They are degenerate. The solutions above, in example 1411, hint that symmetry has a great deal to do with the number of truly unique vibrational degrees of freedom. Consider benzene, which is planar and has D sub 6H symmetry. Because of its symmetry, certain vibrations of benzene are identical to each other and have the same vibrational frequency. This means they have fewer than 30 unique vibrational frequencies in this molecule. There are, in fact, only 20 unique frequencies. Symmetry will have similar ramifications for vibrations in molecules too. Section 14.9. The normal modes of vibration. The vibrations of all molecules can be described in terms of independent motions, such that for each motion the frequency of vibration for all the atoms is the same. These are the normal modes of vibration. Why are the normal modes so important? There are several reasons, but perhaps the most important one is this. To a good approximation, the frequencies of light that are absorbed due to the vibrational motions of the atoms in molecules are those that have the same frequencies as normal modes of vibration.